Today I'm going to talk about basically some practices that we discovered over a period of time working on Kubernetes. This is mainly around, so there are a lot of things you might need to do apart from just the availability. But this talk is mainly around the apps, the good practices, so that you improve the availability of the applications and reduce the error rates for most of the workloads that you might actually deploy on Kubernetes. A lot of them are I have chosen things that are kind of maybe not that well known. So you might not see everything that is related to the availability, and it won't be possible to cover everything. But yeah, some of these are very specific to Kubernetes. Okay, so this is the high level agenda. The reason I laid it out is to also give a overview of where you are in the talk and basically what we are talking at any given point of time. So in this case, we will basically start with very low level. We start at the container, see that if the container itself correctly configured in terms of managing the traffic that is coming to the application. Then we move into the pod level, talk about the readiness, liveliness. There are a lot of issues in there as well. Ensuring that the application, when it is actually serving the traffic, or when the traffic actually reaches or hits the pods, then they are ready to essentially serve the traffic. Then we will move into the graceful shutdowns, which is like two reasons you might end up doing shutdowns. One is you remove the scaling scale out essentially, or you perform rollouts. At that point of time, you because you are putting in new versions, you have to be very sure that the versions actually works. So, and while doing that, your users does not basically see any changes. So there is no spikes in error rates. There is nothing happening there. So those kind of things you have to be careful when you are doing shutdowns. So this is till this it's a pod level. Once you move into services that also are exposed outside, things like gateways, ingress controllers, and all that, they are also coupled with the cloud-based load balancers. And it further becomes tricky because the cloud-based load balancers, their default mode of working are different than the pod level working or the container level working. So if they are not configured correctly, you basically end up the workloads might actually be rolled out when the load balancers haven't even seen the changes. So there are a lot of issues there as well. Then we will move into, so this till this it's all pod level. Then we move into deployments kind of a thing, like how do we schedule the pods? Okay, what strategy do we have to ensure high availability? Then we can talk about the deployment strategies. Post that, we have disturbances. So these are things that are going on in the cluster for various reasons. So this can be voluntary or involuntary disturbances. And then what strategies you can put in to ensure that your workloads are not disturbed that much. Disturbances we might or might not go into depending on how we are doing on the time. Okay, so let's start with container processes. So in general, if you see Unix processes, you are essentially managing the processes. If you see, if you just list out the process, you will see that there is a PID and there is a parent ID for that process. So every process has a kind of a parent, and it's a tree like this. So there are a lot of things that the parent is supposed to do to manage the child processes. But one of them that we are going to focus on is basically managing and forwarding the OS signals. Okay, so whenever you pass in any signals like sick term, sick kills, those signals has to be forwarded. If they are essentially reached at the parent level, they have to be forwarded to the child processes. Okay. Unless you do that correctly, your child processes have no idea what is going on. Okay. So that is basically baked into the Unix processes. Now, when you run your container, so for example, this is something you might put in as an entry point for your basically the Docker file. Okay, in this case, we are saying that the command is basically the bash minus the Java ops, some Java ops. So this is coming from the environment, and then you have the application jar. Okay, if you go inside and list down the PIDs here or the processes, you will see that bash sh is actually running as a PID one, and the Java minus jar is actually running as PID 7. Okay, and you can also see that PID 7 has a parent ID as 1. Okay, so that becomes the parent of this particular thing. The PS minus EF is what the command is that is showing this output. Okay, so there are two processes that are going on. So in this case, your PID is actually the SH, the shell, and not the Java process. Okay. Now what happens is what we want have an ability to do graceful shutdowns. That means when you are actually doing a process of shutting down, you essentially will so K8s as a container orchestration will actually send you those signals, or rather it will send it to the PID one. Okay, the container process, the main container process, which is the PID one. Now so you will get the sig term and other processes to do a graceful shutdown at the container level. So PID one is the process which will actually get that signals from the Kubernetes, and then it is supposed to forward those signals to the actual childs to carry out the graceful shutdown. If you actually do like run any application like Java or like Spring application, any of this, all new frameworks have been coded out for handling the signals. Okay, so if you do a kill minus sig term or something and then send it to the process, you will actually see the shutdown that is happening. So it will actually do the proper shutdown, close any connections, anything like that, and terminate the whole process. Okay. So any DB connections, everything will be handled as part of that process. Or any other shutdown hooks you might have added will actually be carried out as that process. But for that, you will actually need that sector. And the issue that we see in that container that we just saw is that your shell or bash does not actually forward any signal. So it's not a very good parent. Okay, from the container point of view. So you will not receive anything. Okay, what eventually will happen is you will get a sick kill at the parent level, which is in turn will actually kill everything on the container. So it's like just kill. Okay, there is no graceful shutdown or anything like that that will happen. So this is one of the blog. It is published by GitLab. They were seeing a lot of issues because exactly this issue, PID1 issue. And you might not even realize that you are actually doing that. If you go back to the command that we saw, in this case, at least we are doing bash minus C, okay? You will see that even if you don't do it, okay, uh, you might still be using bash inside or shell, to be honest. So if you use this CMD in your Docker file, in this case, you can see that there are actually two separate formats. One is I'm just writing it as it is as a command, normal command, CMD and the command. Okay. And in the second one, we are actually using a separate kind of a array kind of a format to put in the command. And both of them are completely different. There is one more difference, but right now just focus on the, so first one is the shell format. So it is set to be shell format because it will actually use the shell. So in this case, you don't even know that you are actually using shell. Okay, but it will be executed as a shell command. Okay, and then the second one is the execute format, in which you basically are putting in the process that you want to run as part of the container. And the PIDs for these will be completely different. The first one will be PID one will be the shell. The second one will actually run the Java program as a PID one. That means then there is no parent essentially. So you will receive all the signals directly from the Kubernetes. Now one of the issue in, so if you see what is the difference between first and second apart from the format, why will you end up, so you will just say that always use the exec format, right? Why will you end up doing that? Any guesses? Sorry.
First one is very easy to read and write. Everyone will try to do that.
Easy to read is one, but there is a difference. What is the difference? You can see the difference, right? What is the difference? Java ops, right? So the Java ops, if you put in the second command, because there is no shell, there is no expansion that will happen. Okay, basically you are not going to get that Java ops because shell is not there, and shell is where you get the environments and then it basically expands it for you as a command. So if you are using some kind, so that's why people end up using this, and then they don't realize that my process is no more PID one. It is not receiving the signals anymore. Okay, so one of the option to actually mitigate that is to use a exec command. So what exec command does is it actually swaps the children or the child process with, with the parent. Okay, so in this case, it will actually execute with the shell, do the replacement and everything, but then replace the shell with the Java command or the Java process. So in this, the last one, you will not end up with a process with a shell and then the process. There will not be any parent. Your Java will run as a PID one. Okay, and if you have seen or observed a lot of Docker files, they have an entry point.sh, and at the very end, you will see that exec is being used to actually replace. I don't know how many of you actually went and look at it, but the exe one is the trick that actually does allows you to do a lot of shell scripting and then actually replace the final command that you might want to execute and get rid of the shell in between. Okay. That is one option. Another option is to actually use a init process that is designed for the container init kind of a thing. So it is designed to be PID. One of the example is something called as a tiny, okay, which is used by some containers or some Docker images that are publicly available. One of the example is Jenkins, or even Docker itself. I think provides you the ability to specify the or control the or introduce a init process. Like Docker has a minus minus init flag that actually controls it. Okay, so all of this is because you basically get these signals and do the graceful shutdown. Okay, so that is about the containers. Then let's move on to the pods. The first thing you will basically want to do to make sure that you are not serving the traffic when the application itself is not yet even up, okay, and serve the errors to the users. First thing you will do is basically add some kind of a probes at the very start to check whether the application is even up or not. Okay, so there are two kinds of or there are actually three kinds of probes right now, but two are generally used. Is that so used is, so you have a liveliness probe and you have a readiness probe. In case of a readiness probe, do we know the difference? Anyone? Why do we need two of them? And what is happening in this?
Get the pod running, but it is not ready to serve. Basically, that application which serves the because liveness just to ensure that the pod is running, readiness is to ensure that it can actually respond to the request.
Yes, there is one more difference, but yes, that is true. So readiness is defined from a point of view of whether the application is ready to serve the traffic, as this is saying. Okay, liveliness is defined from a point of view of whether the application is up as a process. Okay, but there is another difference, which is a crucial difference to basically decide whether I want to use and how to use and all that. So in case of a readiness probe, ensures the application is running before the traffic is sent to it. So it is a readiness probe is essentially making a decision on the traffic. Okay, it is not making any decision on the application. Application might come up and all of that. It might even fail. Okay, or it might look like that it is working, but if the readiness probe says that it's not working, no traffic will reach to that application. Okay, so whatever endpoints you configure or whatever command you configure for readiness check, as long as that is failing, you will not receive any traffic. Okay, so that traffic check is what is done at the readiness things. So that is great because then we don't want to basically serve users when the pod itself or the process itself is not running properly. Okay. So in that case, readiness probe actually allows us to ensure any kind of rolling updates and all of that will actually help. Uh, the readiness probe will actually help to ensure that the traffic is only served from healthy instances and the healthy versions of the pods. Okay. So now the thing is, these both the probes are not only happening at the start of the life cycle of the pod; they are happening throughout. Okay, that means a pod can become non-ready during the lifetime, and the readiness probe will still kick in. Okay, it will still start. Basically, it will detect that pod is not ready anymore for whatever reason, because like running out of memory or any other reasons, heavily loaded or all those things, and then it will basically cut off and say that it is not healthy anymore. No traffic will be sent. That allows it to recover at runtime, not necessarily only at the startup. So startup, great, you know that it is up and running. Even during the peak times and all that, you will know that the pod is actually up and able to serve the traffic. So this is great. There is something else in terms of when you do a rolling update, the readiness probes are further used. We will talk about that. Next one is the liveliness probe. So one of the key thing is, so liveliness probes have no effect on the traffic. Okay, that's why you should also have readiness in place. Rather, you should have readiness regardless. Liveliness is tricky to manage. Okay. In case of liveliness, it's a mechanism to basically detect the issues and recover the pod from it. Okay. And generally, those are the things that, so there are two philosophies in the fault tolerance kind of a thing. Okay. If the process is, if there is an error basically, then one of the philosophy is just crash. Okay. Don't handle anything, just crash. And then you should have a manager that will actually restore you as a process. This is something that goes into Erlang kind of a philosophy, that there is a hierarchy of manager, supervisors, and all those, and they basically let the process crash if there is an error, and the supervisor will manage that. In a K8s managed environment, you kind of get that for you, regardless of the language that you are using. So you don't need to use a specific language; you are getting it as part of the platform. Okay, because you are running it on K8s, K8s can actually act as a supervisor or as a manager to ensure that the applications are basically crashed. If it is crashed, it will restore it. Okay, but there are other applications. So if it is crashed and restored, it will automatically be restored. Okay, if it is guaranteed that every crash will actually like stop the container, then you don't need liveliness probe at all. Okay, crash is essentially your pod will be restored automatically for you. But there are few cases in which these applications actually are erroring out, but the process itself never crashes. Okay, it will continue to serve, and like that's the second philosophy of fault tolerance, in which you say that you try to recover from it at the programming level without needing a supervisor or anything like that. You basically do some other things to ensure that you continue to serve. Okay, in that cases, if the pod never crash, it does error out but doesn't crash, then there is no way for the Kubernetes to know apart from the liveliness probe. That's where the liveliness probe essentially comes in. So it's a way to detect that something is going wrong in the pod. Then the process of actually recovering it is to basically kill it and bring it back. Okay, so that's what liveliness probe is doing. Okay, that so if you see the handling of the these two probes are completely different. In case of readiness probe is not touching the pod, even if it is erroring out. The only thing that will happen is it will not serve the traffic. It will not give any traffic. It will not send any traffic to that pod. But that pod will continue to be crashing or whatever. It is not working properly, and the traffic won't be sent, but it will still be there. In case of liveliness, is actually recreating the container. Okay, so it is trying to restore it. But in this case, if you are not careful, you might get into something like crash loop back off, and then it continue to restart. The reason it is doing that is the liveliness probe, because it says that okay, it is not live, but the process does not end. The startup process does not end for whatever reason, and then it kills it, restarts, because it basically is saying that liveliness probe failed. I need to recover it, and it is recovering, but the process itself is taking longer period of time, and then it goes into a loop. So you have to be careful with liveliness pros, because it is directly basically changing the pod. Etc. Readiness, you can almost always use that. Liveliness, you have to ensure that your periods are high enough to let the pods recover. Okay, you don't need to kill them. So that's why I said that you don't need, you shouldn't be too aggressive on the liveliness probes. Okay, in this case you can be aggressive. Readiness probe you can be aggressive, but don't be that aggressive on the liveliness probe. Any guesses on the last one? Any guesses why you don't want to do it in a clustered application? Any application that forms a cluster like Kafka or any databases, distributed databases, they are communicating with each other and forms a cluster. Cassandra cluster, Kafka cluster, any distributed database, Mongo, things like that.
The application itself would be actually communicating with each other, and the liveliness would be improved.
Why is that a problem?
Yeah, because
You want to recover, it's not working.
So the application won't know what is actually killing it. And they you have 3 parts running and 1 part is being killed. Then one liveliness actually kills it. Then the these parts are again.
They will detect it. That's the whole point of cluster. So that is correct. It is disruptive. Can you, why do you want not to be disturbed? In which scenario? So if you say that it's completely gone, why not recover it? That's the argument. Are you getting my point? If it is completely gone, restarting it probably will actually recover it, and then
You have to sync it back with the root.
Mhm.
The other 2 parts are to sync to the newly created part.
The created part.
Yeah, recreated part. I mean, so you have 3 parts. One is being cable, and it is being and it has to sync with the input parts.
It will talk with the existing part. That is kind of that's otherwise, if that is not happening, you won't be able to do any rolling deployments. Okay.
Like something on those lines.
So one of the thing is One of the thing is, if you see all of these probes, they are doing a decision at the pod level. They are not doing any decision at the deployment level. They don't have any understanding of any other pods that is there. Okay, that means if there is a possibility that they will actually kill multiple pods, regardless of other pod are actually getting killed at the same time, which makes them so decisions is local. There is no global decision at the cluster level. That means you can lose members of your clusters beyond the quorum that is required to make it available. Okay. One example is a pod that is not healthy as per liveliness might still be able to do the elections, can still be actually be a voting member. It might not serve anything, but it might still be a voting member. There's no way to know. Okay, if it is a voting member, that means it will contribute to the quorum. And if a pod is already down, let's say there are three pods, you have a quorum essentially. One of them is down for whatever reason and being recovered, so you have two pods. And then one of them is detected as not healthy, but it is still able to vote, then you actually have a quorum. In that case, you don't want to you don't want to kill them. Okay. So you have to be careful with the clustered application. Generally, you want, that's why people are going with the operator and all that. Generally, they want a decision, not at an individual pod, they want a decision at the entire cluster level. So it's like a one high level. And then you detect that is there an issue? Is the services available? Generally, you just raise alarms rather than basically do something yourself, unless you are very sure that what you are doing. Like if the visibility is there, then you can do that. At the pod level, you don't take that decision. So in this case, you will generally raise alarm saying that there is something wrong with this. Go and recover. So now containers are done, pods. We talked about the startup. Now let's talk about the shutdowns at the pod level. Okay, that process is also quite a lot of things go on in there. So let's say that we started with this. You said delete a pod. Okay. Uh, so when you say delete a pod, the request is essentially going to the K8s API. So API server understands that you are asking for pod deletion. So in this case, I have not put in everything, but basically what does API server will do is basically goes into etcd and change the pod status to terminating. Okay, and then rest of the application or rest of the components will start reacting to that. One of them is Kubernetes. Okay, so wherever that pod is running, now it will look at it and say that okay, this pod status is changed in the etcd, and that status is now terminating. So I am supposed to terminate the pod. It's not terminating; it's running. Okay, so that's where the Kubernetes basically will react on the basis of the state change. Then it will start terminating the pod, and that at the end your pod is gone. Okay, very simplified uh, process here. We will go into deep, but right now that's the process. So kubelet has reacted to the pod termination request and terminated the pod. It takes some time to essentially terminate the pod. Okay, at the same time other things are also reacting to the pod termination. So one of them is you don't want to send traffic to the pod that is terminating. Okay, so endpoint slice will basically start reacting to it, because endpoint slices essentially maintains all the endpoints. A list of endpoints are there, which is basically the pod IPs. Okay, a pod that is getting terminated, you don't want that pod to be available for sending the traffic. That's what is maintained by the endpoints basically. So now endpoints will start reacting. It will change the endpoint of that pod, saying that it's basically not ready. Terminating is set to true. Serving is set to true. There are reasons for it. So basically, it is saying that it is terminating now. So other components who are using the endpoints now need to start reacting. Okay, so you can see that it's all observation based or a kind of event based. Everyone is independent. They are just reacting to the state changes. Okay. So in this case, the pods are not basically they start. So endpoint slice will change the endpoint and change the status. Now, when it does that, it basically goes back to the API server, and that ultimately goes into, so endpoint state goes into the etcd in the end through the API server. Now the moment you change the endpoints, kube proxy has to react. So what does the kube proxy is doing? Do you know what is kube proxy is actually doing in the Kubernetes cluster? How is it related to the endpoints? So every service that you create, every service you create also creates an endpoint. An endpoint has a list of endpoints. The endpoint slice has a list of endpoints, which basically stores the IP of every pod. Okay. When you send the traffic to the cluster IP of the service, the traffic actually ends up on the pod or one of the pod. Okay. How is that happening is because of the kube proxy. What kube proxy is doing is it actually changes the IP tables on the cluster nodes, so that whenever the traffic is sent to the service IP, it is routed through the IP tables or the rules of the IP tables to ultimately to the actual pods. Okay, so those rules are configured by the kube proxy. Now, kube proxy has to update the rules so that the traffic no more reaches to a pod that is actually terminating. That's why it is reacting. Okay. So what the moment it says that okay, the endpoint is actually is terminating, then it will react and start changing the IP tables. Okay, on all the nodes. That's where the IP table comes in. There might be some other component that will also react asynchronously at probably the same time in which you are saying that DNS entry shouldn't be there and all those things. So that will also start happening. Okay, or probably ingress and all that. But in this case, do you see any problem? So pod is basically getting deleted at that point. Okay. We see. Sorry.
But they are still.
So all of this mechanism, there is, you can see that there is no centralized coordination. Because this will happen, then that will happen. Nobody is actually doing it. Everyone is just doing their own work. Okay. So the propagation, you don't really know whether the endpoint has reacted enough and ensure that no traffic is being sent to that IP when the pod is already gone. So here the IP tables are not yet updated. So it might be sending traffic to that IP, to pod IP, and the pod is already gone. Okay, and that will lead to issues in terms of when you are doing any deletes or rolling updates and all that, that you will end up with errors at the user side. Okay, so all of this is basically there is no centralized coordination. So you don't, the pod might be gone, but the traffic might still reach. Okay. So now we have to look at, is there anything that we can do to ensure that that does not happen? Can we prolong and keep the pod at least till we are basically, so pod should be there for longer before rest of the things actually react. So it is still not completely like visible and you can't coordinate it, but you can tune it in terms of the termination process. Okay. So let's look at the termination process a bit more. So earlier we said that kubelet and then just the termination. Now we are looking at it in more steps. Okay. And the essentially time flows vertically. It's downward. So your pod is deleted. It goes to the Kubernetes API server, goes into etcd, which is then picked up by the kubelet. Now kubelet knows that it needs to terminate the pod. Now what it does is, it basically starts a countdown for the pod. So that is called as a grace period. So it starts a countdown saying that, so it is giving a period to the pod or the container process to gracefully terminate essentially. So after once you start the countdown period, it will also call something called as a pre-stop hook. Okay, so there are few hooks that are given by Kubernetes. Pre-stop, post start, those are the life cycle hooks at the pod level. Okay, one of them is the pre-stop. Pre-stop is a basically a hook that is called, as the name suggests, before stopping the pod. Okay, so it allows you to react to the situation of termination. Okay, so that hook is called. So Once the grace period, so first it will start the grace period, then it will basically call this hook. Once that hook is done, then it will send the termination. So sick term is sent to the process. That means now it should start terminating the process. Okay. Till that the process is not actually terminating. Okay. And then ultimately after a while, it will send the sick kill if it is still running. Okay. If it is terminated, then that's it. We don't need to do anything. But if it is still running, it will basically then say like time's up, go away, and it will kill the kill the pod, and that will ultimately basically be treated as pod gone. Okay. Now in this case, the whole start countdown from the grace period till sending the sick kill is controlled by something called a termination grace period seconds. This is a configuration that you can do at the pod level or the deployment level in which you define the pod template. Okay. So the grace period controls the process or the length of the process. You can increase it, decrease it, you can experiment with that. The other one is that till this point, when it actually shutting down and the rest of the things are reacting in which they are stopping the traffic and all of that, you want to be continue to be serving. Okay. Because you are marked as terminating, the endpoint knows that you are terminating, it is trying to react to it. So you, after a while, you will not receive any, once everyone is basically reacted to it, you will not receive any traffic. Even if you are up, you won't receive any traffic. So you have to be up for a period in which you might actually receive traffic, in which other components are actually reacting. So you can see that till this point, there is no sick term. So your process is not actually going down. It is still serving. Okay, so this is a period for you to continue to serve the traffic. Okay, you don't want to serve errors to the end user. So that is a period which allows you to essentially. So then we should be able to do something in that pre-stop hook. So this is not in our hand, but this we can increase or decrease to control the traffic serving period. Okay, so we should be able to do something in the pre-stop hook. Grace period termination is basically your process is anyway going out. So these are the two things that allows you to control the process, how much time it takes, and we have enough ways to ensure that there is no errors generated as part of the termination process. Okay. Okay, so one of the very simple thing people used to do or generally do is just add a sleep for pre-stop hook. Basically, it is so pod is still running, everything is going on great. You just say that okay, wait for this much amount of time, while rest of the things are basically doing whatever they want to do. So they are essentially putting in some sleep so that the pod will continue to run, but the process of termination basically is delayed for whatever period of time that you are putting in the configuration. Okay, so you don't need to do any special thing in there. So what this is what we already talked. So what you can do is these are two things that you have. So these are directly the seconds. Okay, you just configure it in the pod specification. And that's it. Your grace period will be given to you that much. And the pre-stop hook is what you put in as part of the life cycle for loop. Okay. So these two controls basically allows you to control whether you are up for serving the traffic whenever it is coming in, and how much period you will be there to ensure that the whole process goes through smoothly. Okay. So pre-stop hook, you have to make sure that time taken to stop the traffic, which is rest of the things reacting, and time required to complete the ongoing request. Most of the time, the requests are served quite quickly. So none of this, whatever I'm talking about here, none of this includes any services that are long running, like a bad job or something like that. What I'm talking about here is services that are actually serving a HTTP kind of a traffic, which is like in seconds or milliseconds most of the time. Okay, so it won't be taking that much of time. Okay. Well, you have to be careful on one thing is all of this will slow down the rolling process. So you have to basically experiment and basically check that how much is good enough. So now this process was anyway quite complex. Now you put in one more variable, which is the cloud load balancer. So till now we just talked about service, but when we just assumed a normal cluster IP service, okay, of type cluster IP. But here now we are saying that it is actually using a load balancer service. That means there is a load balancer provisioned in the cloud for you while you are probably performing rolling updates or any terminations and all those things. Okay. Now one more variable comes in. So consider a scenario that you are doing a rolling update, and this has happened with us on projects. Okay. You roll out a new pod that takes like very small amount of time. It's a container in the end. Okay, it takes load balancer controller. So it takes a lot of time to basically for the controller to figure out that there is a healthy pod. Okay, because the default configurations for most of the load balancers in the clouds are basically as per the instances, as per the VMs, not as per the containers. Okay, so VMs generally take a long period of time. So instance comes up, it will take some time, but for containers, it will actually come up quite fast. So that means your default configuration for the load balancer is quite slow for the containers rolling process. They won't be able to detect the changes that are happening. So things that are going on unhealthy and things that are coming in, the new things to which you should start sending the traffic, it won't see those changes. And that is what is happening. It won't detect that new things are healthy, but the content, the process on the Kubernetes side will say, okay, this is healthy. So I should start terminating the old pods. Okay. And then you will see that, okay, there are a lot of errors that are generating as part of rolling deployment. And this is generally more crucial because you are now rolling a gateway kind of a service. Okay, it might be an ingress controller, Nginx or something like that. It might be a Kong or something. And if you end up doing that, a lot of services will start giving you errors. Okay, so it's not a very good way of managing the production traffic. Yeah, all of this might happen. Okay, so one of the way to make sure that pods don't basically go away very easily is to ensure that your LB health intervals and basically to manage both of those and ensure that the pod remains more than the what time taken by the LB. So basically you will change on the other side as well. You will change the intervals on the LB side as well. Okay, you will reduce it, but you will also ensure the pod remains there so that it happens in coordination. There are other ways to do similar things. There is something called as a readiness gate, which is being used by AWS load balancer controller. If you end up using that, so what it is happening is you can add some arbitrary readiness gate. Okay? You can make up anything. There is a syntax for this or the format, but the content can be anything. So in this case, you are just saying that example.com feature one is the condition. Okay, for the pods to basically say that they are ready. Okay. Now in this case, in the status and condition, if you see the container itself is ready, okay, container is marked as ready, but the pod is marked as ready false. Okay, so it is not ready yet. A pod is not considered ready, though the container themselves are actually ready. Okay, now why it is not ready? Because this is marked as false. Okay, so when it starts up, by default this will be false. Whichever condition that you put in will be marked as false. Then you have to basically perform a separate operation uh, as a process. It might be automated, manual, whatever, in which you will patch the pod and change the status at the status level with true. Then the pod will be treated as a true thing. That's where the LB controllers, the newer LB controllers started using this, in which they detect that the pod is considered to be healthy and was seen by the by the load balancer, and then basically you change the you pass the pod to change the status. Okay. So now we talked about the pods, we talked about the containers, we talked about the pods, startup, grace down, all those things. Now we are moving into kind of a higher multiple pods kind of thing. Okay, so now this is basically, yeah.
There is one question I have about the load balancing. Like you said, any cloud load balancer will only forward traffic to instances to a specific instance. And if we are using a cluster, then it means there's only a few instances, like the ingress controller or whatever node contains. That is why I have forward traffic. So which means anyway cluster is doing its own thing.
Cluster?
The Kubernetes cluster will be doing its own load balancing at the ingress level.
At the ingress level. It is not doing it at the ingress level. So what ingress is, so if you see the ingress configuration, there are two things here. Okay, I'm talking about, let's say the traffic is reached to the ingress. What ingress is doing is ingress is sending it to downstream services, which is again a Kubernetes service. The service in turn is actually doing the load balance through IP tables, the kube proxy. Okay, so it basically does sending it to one of the pod and does the round robin and all that. Okay, so service is doing the or service routing is essentially doing the load balancing for you, not the ingress. Ingress is sending it to the service. Service in turn is managing how it should be sent to the pods. Okay, that is one. Another is there is a service in front of the Nginx as well, or the ingress controller as well. Okay, whichever ingress controller you are using, there is a service in front of it. Generally, this service is configured as a load balancer service. Okay, that service, because it's a load balancer, now load balancer is doing load balancing between the pods of the ingress control. I don't know whether I'm clear enough. Am I clear enough? Okay. So that's how the load balancing is working. But that's a different thing altogether. But coming back to the scheduling pod. Okay. So now we talked about the pods. Let's talk about multiple pods. So what is important for ensuring this service is up? What will you essentially do? High availability. What do you want? Okay. You don't want all the pods in the same node and that node goes away. The service is gone. So even if you have multiple pods, it's of no use. So you want to ensure that you spread across multiple nodes bare minimum. Okay. Older clusters, you would do something with pod affinity, anti-affinity kind of a mechanism, in which you basically, so in this case, you are saying that I prefer that, so you are essentially putting in the anti-affinity with yourself. Okay, so any other pod that has the same labels, you don't want to be scheduled on the same node where there is a pod with the same labels. Okay, that's what you are saying here. Okay, so that way you the scheduler will say that okay, there is already a pod of this particular application. Then it will basically choose a different node if it is available. Again, this is preferred. That means you are saying that if there is no other node that matches the criteria for whatever reason, let's say you have three nodes, three pods. So the fourth one has to be somewhere on one of the three nodes. Okay, so 3 times it will do it right. The fourth time it can't. So you have two choices in that. Either you say don't schedule. Okay, in that case you will not say preferred, you will say required. Okay, and then it will be pending, it won't be scheduled. Or you will say preferred, that means scheduler will see that there is no other choice but to break the rule, and then it will basically go ahead and still run the pod on one of the node. All the choices are equal in that case. But this is generally done on an older cluster. Nowadays, you are moving into something called a topology spread. Okay, so in this case, you are essentially defining the. So what Kubernetes started doing for a period of time is you can define topology of the cluster. Okay, that means how the nodes are laid out in terms of how they are distributed. Okay. And so you can also bring in the information of the availability zones and all that from the underlying cloud providers into the cluster topology. Okay, you can tell all of this information to the Kubernetes. Okay, so that way what happens is now Kubernetes knows a lot more in terms of the layout of the cluster. Okay, so now in this case what you are doing is you are saying there are two rules for the spread, topology spread. One of them is you are saying that, so this one, let's talk about this one part. One of them is you are saying that there is a label on the node called node. The node itself is the label on the node. Okay. You should not schedule if that label is saved. Okay. And then there are other labels, but basically it is saying that don't schedule on the same node. Okay. And the second one is again, so this is at the node level and that is at the zone level. So you can also basically tell it to Kubernetes that these are different zones. So set of services will belong to one zone. And then you can map it to the availability zones of your cloud providers. Okay, like AWS availability AZs, you can just directly say that, okay, these nodes have this zone. This node has this zone. This node has this. Now suddenly Kubernetes knows this information. Okay, through labels. And then you can make decisions or ask scheduler to make decisions on the basis of the structure of the or the topology of the cluster. Okay. So in this case, you are saying that don't schedule on the same nodes and also don't schedule on the same zone. That means you are now spreading across zones. Okay. And then there is a max queue. Max queue is again the same situation in which you are essentially like 3 nodes, 3 zones, all of that. Then you have 4 pods. So if you schedule, you are breaking one of the rules. So how many pods it is okay to break the rule? That is what this queue is. Okay, so the fourth one goes into one of the node, but the fifth one won't go into the same node because then the max queue will be 2. So that it will actually choose some other node to run. So out of 3 nodes, there are 2 pods running here. If the scheduler ends up choosing this one, the max queue will be 2. But if it is choosing any of these 2, the max queue will still be 1. Okay, so those are the deployment, those are the scheduling strategies. Okay, you want to spread and all that. Then we move into the deployment strategies. One of them is like a rolling update that you all by default do because they default at the deployment level. You can also get creative and do something else like blue green or like canary releases and all that. There are controllers as well that does it for you. Rather than you doing it manually, I can show you one of them. But the techniques is same. So how do you automate is all up to you. So in case of, so I'm not talking about rolling deployment because most of you already know there are few changes. Uh, I might not talk about those, but there are few changes between how the rolling deployment is done for the deployments and how the rolling deployment is done for the stateful sets, because these are like two completely different things. One is services themselves are stateful. Another is like you can add as many pods and all those. Okay, so the rolling deployments are completely different for both of them. But let's talk about, so rolling deployment, I'm assuming that you already know. So that's why I'm not talking about that. So let's talk about something like a blue-green kind of a deployment. Okay. So as simple as this, you have a service, you have a replica set that is managing pods. Okay. Generally, you use a replica set rather than a deployment because deployment in turn is actually using multiple replica sets. Okay, so it gives you ability to roll back and do all kinds of things. But here, because you are managing the changes in the pods, either automated with some process or manually, so you probably don't need a deployment. You can still do it with the deployment if you want to, but then you shouldn't be using some of the things that the deployment allows you to do. Okay, right, like rolling back and all that, because you are not using it like that. Okay. So simple one service using the latest It is supposed to be blue. I don't know whether you can see the color. Okay, and this is supposed to be, I don't know why the colors are different. It's supposed to be green. Okay, blue green, right? But here, so this is a new replica set, new version of the pods and all that. Generally, you will not touch the first one. Okay, you will do it as a separate deployment. So it is available, but it's not being served. You can also have a service to test it if you want. Okay, so you have a service in front, and then you can use that service to test everything is correct, great, and then you start the switching basically. So till now, all the actual traffic is going to the main service, the older version, and this is all test traffic or whichever way you want to verify. Okay. Then you basically switch over. When you are switching over, you basically change the service YAML essentially, and you change the labels. Okay, the moment you change the labels, it will start looking at the new pods rather than the old pods. It will do this shift. So all of this will happen. In the meantime, what can happen? When you are switching, what can happen? So you made a change, that change goes, the rest of the system is still reacting.
Partially to older and the traffic gets routed to partially older.
So there is a possibility that the traffic will still end up, some traffic will still end up on the old version. Okay, so that means you have to make sure when you switch, the old version is still running. Don't destroy it, because traffic might still come there. Okay, the switch will happen after a while. Okay, now all the traffic is on the new. So we basically done the switch essentially. And the last one is in which might have guessed is you basically get rid of the old replica set altogether. Okay. In this case, the onus of rolling back is on you if you are using replica set, because replica set doesn't give you an ability to roll back. Okay, so you need mechanism to ensure that there is versioning, there is the ability to actually go back to the older state and all that. Okay. If you are using deployments, you can roll back, but then you have to manage other things because you are doing two things. Okay. So manage according to that. But now you essentially done a kind of a blue-green, and you can keep the. So in what is happening in this is, for a while the older and new versions coexist as part of it. Even in case of rolling deployment, that happens, but that is quite fast and automated. If your newer pod comes up like fast enough, the older pods are removed. So you don't have a say that keep the older pods while I have the newer pods. They might be actually serving the traffic, but I still have the older. So sometimes you can actually keep it for a longer period of time just to do the rollback if you want. Okay. But the main thing is basically you have two versions of the same application running in the cluster. Okay, so end result is basically this. Once you are happy with the new version and everything goes through. Further thing that you can probably do is something like a canary releases. Before we go in there, any differences, why there is two type, blue, green, canary, separate, same, rolling deployment, same.
Like, why do we have canary?
What is the difference?
Just like you're like totally jumping from 0 to 1, there is no state in.
Yes. So in case of like when people like first you just take downtime and then bring up the new one and all that, then people realize you don't want to do that. So they started doing rolling deployments or something like that. Then they said that okay, I want to still have the older thing. I want to be able to test it. It should be there, but it shouldn't be serving traffic and all that. So then you have a way to switch. Then they realize that okay, I need probably more. Okay, and that's why as you said that I don't want the entire traffic going to the new one. I want only subset of it. Okay. And then there are other multiple ways of doing this. You can basically do some maths and figure out how many requests should go here and there, but there is easy way as well, which I am showing. Okay. So in this case, you have like old replica set, new replica set, all of this in place. You can see that there are 4 pods there. There is nothing here, so no traffic is going here. Service is same, and then you basically do the rolling manually. Say a few pods. Either you do it manually or you automate all this process. There are pre-checks or some checks, or there is some duration that you put in and see the error logs and all that, or you do it every step manually. It's all up to you. Okay, there are ways to carry out the whole process. Okay, but all you are doing is basically this process. Okay. So in this case, you basically said that okay, there are 3 pods. There is only 1 pod on this side. So some traffic is actually being served from the new one, and then you go and check whether there are errors. Everything is working fine, but the impact is minimized because you only serve few of the things. So your confidence goes up. You say, okay, it looks good. You continue to do the process. Now you are 50-50. Then you basically move. Eventually, you go into the new things. You can retain the old for a while to come back if you want to, or you can get rid of it. Okay. There are few controllers that are there. So I don't know whether if you go and look at Argo CD, that gives you both the controllers for you. Especially the canary one gives you ability to do the traffic management, and then it will give you the delay and everything. I can show you that documentation, or maybe you can look it up. But it is doing something similar. Okay, so it's all configuration. You say that okay, do this, then do the shift, then wait for this much time, then do the another, do that, and then you can also say infinitely stop here, and then you have to do something manually later. Do we have time? Want to talk about this, or we have time? Okay, I will go through this as fast as possible. So disturbances is another thing that you should be aware of, because all of this happens and then people basically see, okay, this happened, that happened. And if your trust is not properly configured, a lot of things goes wrong, and then you lose the confidence in the cluster. Okay. So there are 2 kinds of disturbances: voluntary, involuntary. Voluntary is something, some process is causing the disturbance, like you are draining a node, you are taking out a node, or deleting a node, or something like that. You are doing a rolling deployments, that is also a kind of a disturbance. You are deleting a pod. All of these are disturbances. Evicting a pod is another. You want to move one pod from one node to another and all that for whatever reason. Okay, so draining in a way does that for all the pods, but you can basically choose to do only for one of them. So that's a eviction. So it can be voluntary or it can be involuntary. Okay, something like this, in which node is out of resources, there is hardware failure, there is disk pressures and all kinds of things. Okay, then there are involuntary also includes preemption. So there are 2 processes I will talk about: eviction and preemption. Before that, so in case of voluntary disturbances, at least Kubernetes gives you some control on it because it's voluntary. Okay. So in case of voluntary, you can define something called as a pod disruption budget. So as the name suggests, it is basically giving you some budget to spend in terms of disturbances, but you can't overspend. Okay, you have a budget, a limit. So in this case, we are saying that zookeeper max unavailable is 1, and now this is not doing a local decision. Okay, it is doing across the pods. So all the pods that matches this level will basically be counted in the availability wala cheez. Okay, so that means you have 3 pods, one of them is unavailable, then it will be marked as unavailable. Okay, and then that will be counted against the budget. And once that happens, then if you try to do something with the other 2, it will basically stop you. It won't allow you to do voluntary disturbance. If there is a pressure on all that, it will basically still go. But at least for voluntary, you can control the disturbance that might happen. So anything that is very important, like stateful things and all that, you want an ability to control the disturbances that might happen to your workloads. Okay, so this is one way of managing that. In case of involuntary, these are the things. So let's talk about both the processes. First one is eviction, another is the preemption. So any guesses? I've written some things here, but any guesses? Eviction, preemption, what is going on? Why do you need two things for the same? Probably same. So what is happening in case of eviction is something that is happening at a node level. Okay, something goes wrong. Okay, now node might be running out of memory, out of CPU, all those kind of things, and whatever number of pods it is running, it can't basically support those many. So what it start doing is it actually start moving things out. Okay, say that I don't want this pod to be running, so it will start reducing. It won't reduce everything. Okay, it will start doing it one by one till the pressure is on. Okay, and then there is a whole kind of process there. I'm not going to go into that, but it will start basically moving things around. It will say evict this pod, it will go somewhere else, but I can't basically manage this thing. So start removing the workloads. That is a process of eviction. Who is doing that in a Kubernetes cluster? Which process will actually do it? Which component will do it? Sorry?
What the thing? Some control and few control.
It is happening on worker. Which one? Kubelet. Okay, kubelet is basically going to react to the eviction. The whole process is carried out by the kubelet process. In case of a preemption, what is happening is there is a high priority pod, and then there is a low priority pod that is running. And the high priority pod does not find place to actually run. When this is happening, this is the scheduling time. It's trying to schedule the pod, and there is no space. But this is a high priority pod, and there is a low priority pod. So it will actually do preemption. It will remove the low priority pod. It will schedule the high priority pod at that point of time, at that place, and then basically the low priority pod will then be pending. If it finds place somewhere else, great, or otherwise it will just be remaining as pending. Okay, so who will be doing the preemption? Which component will do the preemption? Is it again kubelet? Scheduler will do it. So these are like two different processes. That's why they are named differently. They are managed by different things, and the reasons are different altogether. So preemption is being done by the scheduler, because it's a scheduling time event. It will only happen during the scheduling. The eviction can happen anytime, and it will be done by the kubelet. So how do I reduce the impact of the involuntary disturbances? So I don't know whether I should go in terms of this. So there is something called as quality of service. When I say that eviction process starts, it actually start choosing the pods to remove. Okay, and then there is some criteria in which it says that these are the worst pods. I don't want this. Okay, that is what is the quality of service. There are three quality of or three buckets in which the pods are basically laid out: guaranteed, bus stable, and best effort. Okay, I will quickly show you how is that defined. So in case of a guaranteed pod, the resources of that pod will look something like this, exactly same. Okay, so it is saying that I want this much, and this is my limit as well. So there is no overcommitment. Scheduling happens on the basis of request. Okay, if you have this much, your pod will be started on that node, but that does not mean that you are only going to eat up this much. You might eat up like whatever you want. So for example, if you are saying that I need 2 GB, but my limit is 10 GB, and if there is a node that has 3 GB, the scheduler will still run you there, but you will eat up all 3 GB and say that now there is nothing there. Okay, and that will kill the whole node. Okay, so you are not a good citizen of that node. You will be kicked out. But guaranteed pods are the great citizens. Okay, they will be the last to be kicked out of eviction process. So these are like guaranteed. You're basically giving a guarantee to the things that I won't go beyond. Okay. Then there is a bustable. Means there is a difference. Okay. And bustable is not a category, it's more like a range. Okay. Like you can be very close to each other, you're still bustable, but you are still a good or okay citizen. People who have like or the pods that has very variation in the request and limits, those are like on the worst side of things. So it's like a spectrum rather than a single thing, but it's all bustable. Okay. And then there is further worst. What will be the worst than this?
10x of the
Huh?
if you're using like 10x of the
That is still bustable, na? Sorry, infinity. Okay. How do you define infinity here?
It's an option.
Sorry,
It's an option.
it is.
It's an option.
Limits are optional, na? Oh yeah. So that's basically the best effort. You're basically not telling anything. Okay. So in this case, at least I have put in some request. There's no limit, but you can also have no requests. So there is no idea for the Kubernetes to figure out what do you even need. That is the best effort. So it is doing the best effort that it can, but you will be the first one to be kicked out. Okay. So don't use bustable or even best effort on the wrong spectrum in your production workload. It will be a hell to manage those clusters. You want to be as close to the guaranteed as possible. Then there is, if you see, so QoS we talked. There is a second thing that is cluster auto scaling. So I'm not talking about the scaling as such at the pod level, but this is one thing that probably you might not know. Scaling you will probably know. Okay. In this case, cluster autoscaler, generally you want to have an ability. So you scale the pods, but there are no nodes to even run those pods. So what is the point of scaling? They are all pending. So you want an ability to quickly schedule them. How will you actually do that? One of the things that we already talked about. What is that we talked about? One process we talked about already regarding the scheduling thing. Preemption. So you can use preemption to reserve the quota. Okay. So something like, so what you can do is you can create a priority class and basically say that the value is -1. Okay, so it's a lower value. So this is a over provisioner. Okay. And this is a low priority pod. Okay, and then you can have a pod like this that is using some like POSBIS kind of container that will remain there. See the amount of CPU memory you are giving is huge. Okay, because it is reserving a single additional node. It is running on that node, keeping it running. Okay, but it's an additional reserved node. Okay, but because it is using the priority class that is low, then the rest of the workload it will be kicked out, and then the scheduler will actually run your pod there. So you are not waiting for the node to be provisioned. Because this pod gets kicked out, it's a big pod, so it needs the entire node. Because of that node, the cluster autoscaler will start adding a node. Because now this pod is actually pending, but your actual service pods are not pending. So your process of adding nodes is kicked in because of this pod, but this because the preemption of this pod, the actual service pods can get scheduled. So you can actually use this thing. Yeah, this is the last.
But we also have to schedule the preemption rules priority for all the other parts, right?
By default, there is.
It is higher than this one.
So by default, it is 0. That's why
Oh.
this one is -1. Okay. So it is already there. So you don't need to do anything. And the last one is the pod disruption budget cannot prevent the involuntary, but it does count it. Okay, so that means if something is lost, it can't stop it. It is lost, but it will still know that it is lost. So it won't allow you to do voluntary disturbances to other parts. Okay. So that's the last thing in terms of managing the disturbance. I think that's all I have.